Hello, everyone. Good morning. I am pleased to welcome Professor Dimitrios Kalliontzis. He is an assistant professor in civil and environmental engineering at the University of Houston. His research combines structural and multiphysics engineering concepts to understand and improve the behavior of civil and marine energy systems. Dimitrios is currently serving in the board of directors of the University Marine Energy Research Community and is a member of ACI committees, including 239, 357, and 550. Prior to joining the University of Houston, he was a postdoctoral researcher at UC San Diego, and he earned his PhD degree before from the University of Minnesota. The title of the talk is Multiphysics Effects in Understanding Fluid Structure Interaction, FSI, Phenomena for Civil and Marine Energy Systems. Thank you very much, Dr. Kalliontzis, for doing this, and the stage is all yours.
Thank you so much for the invitation. The talk today is about multiphysics effects. I'm going to talk about fluid structure interaction is going to be central to my talk today. And generally, I'm going to try to define it and then try to see how that can be incorporated and taken into account in several types of problems. So generally, when it comes to fluid structure interaction, it's a multiphysics problem. You have two domains. One is the fluid domain, the solid domain, but you also have the interface domain. So these domains through the interface exchange several information that is important in this fluid structure interaction coupling. Okay, so we have laws on fluids and solids, and those interact. Now, a lot of people would, consider two types of wave of fluid structure interaction. One is typically referred to one way, where basically the fluid domain gives the information through the interface of the structure, but there's no two-way effect, so there's no feedback from the structural domain to the fluid. That is a general precept of what is a one-way FSI. It's typically used when we assume small structural deformations. You have a pretty stiff structure, whatever the structure is, and therefore you can in theory make this assumption that my structure is a bluff body, is a rigid boundary. I don't have to transfer information to define my problem. And then when larger structural deformations occur, then researchers would assume that this is a two-way phenomenon where I do need to transfer the informations back and forth so that I can obtain an accurate estimate of the overall response of the coupled system. So these are just general assumptions. Now, when it comes to fluid structure interaction, we consider several types of phase flow. So we have problems where we can call them like one phase flow, where there's just a single fluid, let's say air, or just water associated with a response. And in this type, I use, an example of a vortex-induced vibration problem that is very common in literature, where you have cases where with small structural deformations, the structure is stiff, the beam in this case is stiff, or versus another case that is large deformation. So in a problem like this, that is a vortex-induced vibration, structural deformation will change the vortex shedding frequency. So, but in this problem, for example, the lift force that could be important in your, in your analysis and design for the structure does not change significantly, is still bounded within the same range. But if you have a problem that frequency is an important aspect of your design, then you should account for these effects. There are also problems that involve two-phase flows. For example, when you have air and water, this is just a simple demonstration that lipid exaggerating the compliant or flexible structure, where you have a rigid structure on the left side. The flow basically impacts, it rises on the structure and then splices back. In the other case, the motion of the structure, the deformation of the structure does affect the flow. So this is a different class of problems, which I'm going to also talk a lot about today. going to mainly focus on two-phase flow problems. The key question in this type of problem is what coupling effects exist in the fluid and structural domain. And as you know, many times we ask is how much, like, are they important? And if they are important, by how much and in what terms? A more practical example of where this type of effects may manifest is elevated structures. Especially at Florida and similarly in Texas, we are very much aware of the hurricane season, and that brings significant storm surge. And after this type of events, we do see a lot of damage. In recent years, we have seen a lot of damage in these structures. This is why a lot of them are elevated one way or another. So these structures, however, do experience sometimes significant wave impact on the first floor elevation because of the storm surge type that increases the free surface elevation significantly so that waves can reach the first elevation. And these structures are flexible inherently. They do have compliance that can come in several forms. One form is the foundation flexibility. So how the piles are designed, what is the embedment length, what is the diameter of its pile, as well as the connections, right? The connections details can vary. To study these effects in this problem, we used light frame elevated coastal structure, a typical design that was developed based on FEMA P 499, among other FEMA guidelines. And we tried to see if waves hit the structure and assuming different compliance effects, degrees of compliance and effects, how the behavior changes. So in order to incorporate the effect of connection compliance, we used two different types of connections. One is a moment connection. You can think about that as a more rigid connection or more stiff connection versus a pin connection that is more flexible. So the effect of soil compliance was also accounted for in this scenario. So I'm not a geotechnical engineer, so structural engineers for the most part would represent this behavior with PY springs. So we did, and we varied the pile design, as I will explain later, by changing the embedment and the pile dimension. So in the first scenario where we accounted for the effect of connection compliance, what we observed basically is that compared to the rigid model, where the structure is practically has the same geometry, but it's just a bluff body, the deformations were, of course, more significant in the flexible structure, but also the contact forces the flexible structure experienced increased significantly in this scenario by 55%. In the meantime, the moment resisting connections also experienced slightly higher forces compared to the rigid model, but not as much, just by 7%. So the solution was much closer to the rigid body model. What we also notice is when flexibility occurs in the structure, the interaction phenomenon is prolonged because the structure bends, so it allows significantly more hydrodynamic impulse to be concentrated in front of the structure and extends the impulse response, and also it shifts the time where the maximum displacement and force occur. In a similar fashion, we explore the effect of soil compliance by changing the design of the piles, basically by increasing or decreasing the embedment length of the piles using embedment length to diameter 5 and 10 ratios. And we also compared to the model with no soil effect. So in this case, we did also observe an increase by 30% depending on the embedment length. And this shows like how the shapes of the response at maximum deformation were depicted by the model. And I want you also to pay attention to the model shapes that were observed, especially for the first elevation facade, because that is an important aspect that we decided that needs further investigation. So generally speaking, this type of shape, which in a way is similar to what you would expect in a simple supported beam, causes a deflection that will trap, in a way, more wave energy in front of the structure that causes this increase in deflection, and force. So generally, in this small study, we did observe a prolonged hydrodynamic momentum transfer as a function of the compliance. We did observe a 50% increase in the peak force of the system. We did observe the soil compliance matters. So anyone who's a geotechnical engineer will be happy about that, in the sense that soil effects do matter in this case. Of course, this study was an initial study where we did not account for material nonlinearities, component failure effects, and other aspects that, of course, will play a role in the behavior. Then after this study, we decided to go back to more fundamental problem where we can study this compliance effect in more depth, but also incorporate another parameter of the boundary conditions, right? So boundary conditions were considered in our hypothesis very important because they do affect the stiffness, but they also affect the modal response. A simple problem that could be used to study this effect is the downbreak problem. It's a problem that has been studied significantly in the literature, used in validation of multi-phase flow models and structural models and so on and so forth. So we decided to use that popular problem in the study. Basically, as you show in the short video on the right side, it involves just the water column that breaks. That's where the downbreak problem definition, the name comes from, and then it hits a structure. In this case, the structure is a cantilever, right? So it has fixed boundary conditions at the bottom, no boundary conditions at the top. And then the structure deflects and then interacts with the structure. So before we got there, we decided to develop a new formulation that we could use for a problem of that sort, using what they call force-based beam column elements. So whoever have used open seas in the past is probably familiar with this type of elements. They are very popular in structural engineering because they do reduce computational costs. You can generally simulate very complex forms of behavior with just a single force-based element. We also decided, after using these elements, to use an interface tracking method to simulate the fluid structure interface. That is a very important aspect in a fluid structure interaction simulation because it basically defines how the two domains communicate. And as you saw, for example, in the top part, it's a simulation from a commercial software that we did with the shell plate and a fluid domain that flows toward the plate. You can have what is called a spurious fluid intrusion, which is not realistic. The fluid, in fact, should interact with the structure and not penetrate it. And this is a problem that is associated on how the interface is simulated. Now, this beam column elements, just the background on this topic, are favorite in structural modeling because you can model like big structures with just a few elements, and within a couple minutes you can get very reliable responses on big systems. So this just shows a bridge pier with a pile foundation system that was modeled as part of my postdoc at UC San Diego. They are very simple. They have just two nodes, right? So you have two nodes, and then you can vary the number of fiber sections depending on the problem of interest. There are many papers written on these topics. This is not a new element type. It has been there out there for a while. For my part of the research, what I did at some point, it was to simulate axial load, flexure, shear interaction, pile system that was pre-stressed using just a single element. And you can see that just by using this type of element, the simulation can be very successful, even for very complicated responses that may take many, many days to run with a more highly refined software. So The key, though, in this type of problem is that since these elements are one-dimensional, right? They're line elements. How do you couple them with a multi-dimensional fluid domain? And then that is the key of the what we call the arbitrary Lagrangian Eulerian formulation with skeleton-based structural modeling approach that we developed in order to achieve this interface model. So this basically accounts for an interface that is modeled in compatible form with the force-based element, and so can allow the use of these elements. Of course, there is a lot of things involved below, behind the scenes. There's a lot of solver architecture behind. We use Julia to write all the codes for this type of problems. This is just some calculations done by my student in terms of the scaling of problems in our framework. This Julia is a new, for those who don't know, is a relatively new, much newer, for example, than Python platform. And so we had to do some more basic simulations to get some data on the speed up of the code. Of course, we did many benchmarking. This just shows like some benchmarking on turbulent flow correlations that my student has done, and many other studies. So to look at how our software works. This is an ongoing work that my student has been doing on the wall of wind problem using this platform. I should say platform, not software, because it's not commercial. It's in-house developed. And with that, I just go back to the problem that we studied. So we decided, as I said, to vary not only the stiffness in the simple problem, but also the boundary conditions as much as we could. I mean, the possibilities here are limitless, but we decided to focus on 6 basic conditions, mainly related to cantilever, simply supported, combinations of roller with a fixed boundary, and a fixed boundary. So what did we observe? We did observe that, as someone would expect, the more flexible, the more compliant the structure is, the larger the deformations. This is an expected response. But when you look at the horizontal forces now, that is a very interesting finding, because generally, based on the initial findings we had, was the more flexible, the larger the forces. However, here, the boundary condition is a significant part. For example, the cantilever, if I go back to this graph, experienced the highest lateral drift friction. Well, it experienced also the lower horizontal force, right? So this is in a way counterintuitive based on what we saw in the beginning, but in fact is because of the boundary condition effect. When you have a cantilever structure, in a way the structure deflects so that it creates a pathway for the flow of the fluid to leave the structure and therefore experience reduced forces. When you have a simply supported condition or a fixed condition, even though you may have the flexure significant compliance within the structural properties, within the mechanical properties of the structure, you in a way trap the wave momentum so that you then end up with much higher horizontal force. In fact, in this case, the highest force was attributed to the roller fixed condition, where the roller is placed at the bottom. And as you can imagine, the resultant of the wave force is located near the bottom part of the structure, and so it results in much higher forces. After that, we did, investigate other aspects, such as the sensitivity to stiffness. As you increase the stiffness, then all the results converge to the same solution, as we'd expected. This is the peak vertical force that we observed in this case. So interestingly, when you have a roller fixed at the top, roller support at the bottom, the structure experiences a vertical force that decreases with the stiffness. When you have a cantilever, the structure, as it deflects, it basically hosts the fluid on the top so that it experiences a vertical downward force. So both cases, there are some vertical forces in the structure depending on the on the level of deformations. Then we looked also some aspects of the fluid kinetic energy, how it varies in front of the structure, and whether it matters. Most structures experience very similar responses. The cantilever was a little bit different, had some prolonged fluid kinetic energy, mainly because it created this pathway on top of it so that it allowed more kinetic energy to stay within the neighboring elements of the structure for longer periods. And the model analysis that we perform in terms of energy force, we also have results for displacement, showed that, depending on the boundary conditions, you have different modal participation in the system. If you look at the right side, which is basically the force exerted by the fluid on the structure. Fluid forces, as you can imagine, they can be scattered significantly. The profiles that they generate of pressure, they are highly nonlinear, and that also reflects on the modes basically that they try to excite. The impact phase, for example, which is the blue hash, you see that they are trying to excite significant number of modes. So the structure, of course, the structure would respond typically within the first two modes at impact, and then depending on the level of deformation, this participation of modes may increase. One other aspect that I feel like also very happy about is that this framework that we developed was then utilized by the Near East Lehigh facility in order to perform real-time hybrid simulation. So the collaborator is Dr. Jim Rickles and the students Faisal Nisar from Lehigh, who basically helped me to, and then they led this work in order to integrate the two frameworks. Of course, when it comes to fluid structure interaction, anyone who has done CFD analysis realizes that it's very time consuming. So the key question is that how can you even consider real-time hybrid simulation? So, well, we were able to achieve that through several aspects. One was related to the ALE-SSM and how it is formulated that allows basically through the force-based elements that have very few nodes to achieve real-time hybrid simulation by basically training the fluid forces through a neural network. So that's the key that allowed this behavior. So in this case, we had the benchmark problem with one cantilever structure and a damper system that was represented experimentally. These are just some results of this problem. So in this case, we accounted for one-phase flows. We just wanted to do a first benchmark, but the significance of this problem, even though it is relatively simple, it does result in excitations that span significant frequency ranges, which is also a topic, an aspect that we wanted to verify that it works through a real-time hybrid simulation, because in reality, if you are trying to simulate either a wind problem or a wave structure interaction problem, you should expect that you have significant range of frequencies. So the question was, can a system like that in real time capture that? And the simulation showed that the original full fluid structure interaction solution matched excellent to the real-time hybrid simulation framework. And I want to emphasize that this happened in real time. It's a real-time hybrid simulation. It's one of the few times that RTHS has been done for this problem, and we plan to continue this line of work. Well, that was just a parenthesis of how we're about our framework and that how it can be extended to other usages. But one aspect that I should say is that a lot of researchers will generally look at numerical results, and the numerical results may say part of the truth. So we decided to also explain this behavior, investigate this behavior through an experimental setup. So in this case, we decided to look at masonry walls that are generally have flexibility inherent to them, and try to see whether if we run a wave flume test in our lab, if we are going to see similar results, or we're going to just see, that all walls that we have in our test setup will behave the same. So we tried to vary the compliance from one wall to another. So we had, for example, walls that are ungrouted with some weaknesses in the mortar joints that introduce additional flexibilities. Also this type of experimental model replicates field solutions where you see, after many years, walls that are located in coastal areas, they do experience some erosion in the mortar joints. And then we also accounted for some of them that had grout with weaknesses in the mortar joints, along with reinforcement in the grout itself. So this is just a video from our test for one of the wave scenarios that we explored. This was basically the failure of wall one that we tested. So this wall, as you see at the bottom side of the slide, experienced basically a mortar joint failure at about a quarter height from the top, and then also at the same time the top joint failed. Then we looked at the deformations of these walls. The first two walls, more flexible, experienced much higher deformations. There's other two walls, much more easy through the grouting and the reinforcement. They experience much lower deflections. Interestingly, then we compared the average impulse responses that reflect basically the forces that experienced in these walls. And we did notice that different walls, as a function of the stiffness, do experience different forces. So in this scenario, you can think about this mode of response of the wall much closer, but not exactly the same, but much closer to a simply supported beam behavior. And so we would expect higher forces in the more flexible cases, which is exactly what we observe here. So in a way, this is an ongoing project, so I don't have more results to show, but overall it provides a first indication that our original assumption about the boundary conditions, the compliance effects, does hold in in both numerics and experience. So far, I have been trying to convince you that two-way FSI is very important, right? So I think many of you have realized that so far. But now I'm going to tell you that two-way FSI may not be the first choice in every single problem that we solve. And the reason is because engineering problems require a significant number of iterations to achieve optimal designs. And then this is the case for many fields. One field is the wave energy, where the first thing you want to do when you design a wave energy converter is not to rely on a very high fidelity, rigorous two-way FSI formulation. What you want to do is have the ability to perform many simulations to be able to end up with a converged optimal design. Then on that specific design, you may perform refinements that may require additional FSI. So generally speaking, in a case like that, which I'm going to just demonstrate the case that we did in our laboratory for a wave energy converter design, you do want to start by simpler, lower fidelity, if you like, medium fidelity methods. So one-way FSI, therefore, may be a worthwhile trade-off between accuracy and computational effort in these scenarios. So many of you may not be familiar with wave energy converters. In fact, we don't have many field applications in the US, not yet. But there are systems that basically try to harvest wave energy. Okay, some of them may be located near existing structures, like ports or platforms in the ocean, or they may just be mobile, standalone structures or arrays in different areas, so offshore areas. So there are different types of them. This is just presents some of them. My research has focused on what we call the MWEC, or multi-mode wave energy converter system, that I will explain in a bit. So wave energy is a highly untapped form of energy that we have in the United States and around the world. In fact, if we were able to harness all this energy, we would be able to cover the energy demands in many areas of the country. Now, the key about wave energy in different aspects is that they try to have a specific primary degree of freedom mode that they want to be excited about. Some of them are following pitch, some of them using heave, some of them use other methodologies, and there are other modes as well that could be accounted for. But the one we are trying to investigate in the study was what we call the multi-mode WEC, which in a way is an under investigated technology that basically tries to harness energy from all three modes, heave, surge, and pitch. So the theoretical capabilities and why we're investigating this wake is because in theory it can achieve threefold energy capture compared to other wakes that rely on a single mode. So in an MWEC, you have all these three modes: surge, heave, and pitch. So surge is basically the horizontal motion, heave is the vertical motion, and pitch is the rotational motion. All of this are being trying to investigate in this case. Of course, before we get there, we need to identify a deployment site where we're going to deploy this device. So our study was very specifically aligned with a specific site. We wanted to have realistic wave field results in order to study this behavior. So we selected the site at Santa Barbara to do the study. Now, fluid structure interaction effects are not completely ignored in a problem like this, right? But they are accounted for in a more linear way. So typically when we want to run many analysis, as I said, for problems like that, we do rely on methods like the boundary element method, other closed form solutions, and so on and so forth. Of course, those methods do have limitations. For example, viscous effects, turbulence effects, if they're important, are not accounted for. They are based on linear wave theory, so there is no wave breaking, and then there is a rigid body motion assumption. So the WEC still moves, right? Still, you still have the motion, but you assume it to be a rigid body in that sense. Now, how does FSI comes into this problem? We have what is called of course, the wave forces that are exerted on the structure. We have the radiation effects that come into through the added mass effects and the what they call radiation damping. So you can think about this as an equation of motion in the frequency domain that you perhaps the students learn in a dynamics course. In that dynamics course, you perhaps not have those two terms, and these two terms is because they come from the effects of the fluid. So the radiation problem basically is that when a body accelerates in fluid, it must also accelerate the surrounding fluid, right? So the equation of motion brings this added mass effect into it that accounts for this fluid structure interaction effect. The second effect relates to damping, okay? So that is not viscous damping that we learn in structural dynamics. It has nothing to do with deformations of the structure, but it has to do with an oscillating body which produces and radiates waves. So as the body oscillates, some of the energy is lost through radiation, which results to a damping effect into the structure. The methodology we followed for this approach was, and generally I think many others may also use similar approaches, is mass optimization of the MWEC. Since we do not have a lot of research on MWEC studies, only just a few papers out there on this topic, we had to optimize and define an optimal shape. Then study modal coupling effects. This is a topic that, in fact, if MWEC studies have been covered in the literature a little bit, modal coupling effects have not covered at all, I would say. And then the power capture, using the hydrodynamic analysis results. What is the power capture in the system? In this type of cases, we have to also ensure hydrostatic stability of the system, along without having to rely on a PTO to provide that. So we had to optimize our structure for both by tuning both the periods to pitch and heave, but also try to ensure optimized density for hydrostatic stability. To do that, we did use the surrogate model approach. So machine learning approaches in general are very important, very handy in coming with a fast and quick solution for mass distribution of WEC systems is what we found. This is just an algorithm that we developed for the mass distribution optimization. I don't want to go into many details, but it provides a fast and quick solutions to this problem. One aspect that I cannot go in many details into, but I think is very important in relation to MWEX is modal coupling and modal varying effects. By modal varying, basically, we mean that a case where two modes may veer away instead of crossing. These are very, in a way, dangerous areas to design, because if you design near those regions, small variations in your in the tolerance of your design may actually give you a response that was significantly off from what you expected. So because of that, I think this is very important areas to identify. And it was, in fact, the first time that someone did a topic like research on this topic for MWEC systems. Basically, what you practically need to know is that don't design along near these areas that may cause veering effects. Okay, so if you design elsewhere, your MWEC will behave fine. Another aspect at the end is power capture, and I think an important observation we have made through our analysis is the so-called destructive interference. So you would think that each single mode in the structure, right, in the MWEC will try to absorb energy. Well, coupling effects result in these negative energy absorptions. In other words, destructive interference in power capture. So we did observe these effects, even though they were not that important, but mainly introduced by pitch and surge modes. Eventually, we did find that these do not manifest themselves in the overall global power capture of the system, but they do occur. And this has to do, again, with modal coupling effects. Finally, what we observed when we did the annual energy production with reference to our site was that basically MWECs are able to distribute the energy absorption over a bandwidth of wave excitations versus a point absorber, which, if designed passively, will mainly focus on be really effective within a very specific wave period, but then its energy absorption will diminish for other regions around. Generally, in this theoretical investigation, we found that the increase in power capture is by 42% higher compared to a point absorber. I think this is an important theoretical basis for further investigating MWECs in the future. Finally, this is just my teaser. Do you still think that does not matter for concrete? So I thought, I was asked not to talk about concrete because part of my research is looking at concrete. And in fact, we have a DOE project that will, at some point, was awarded in 2024, and we expect to start soon on design of WEC hulls using ultra high performance concrete. So, well, like concrete is a fluid, right? Before it becomes a solid, it is a fluid and has characteristics that through the fresh behavior must be studied. And I believe that fluid structure interaction also matters when you especially include fibers in the fluid, right? So when you include fibers in the USB-C, for example, your flow behavior changes. We know that, but we have not studied that to the degree that we should. So even though this is not a talk about concrete, fluid structure interaction can matter about concrete. Some acknowledgements. So the WEC, the wave energy investigation, was performed through a research project that was provided to us through the MSI program, through the WPTA office of DOE. and the wave masonry interactions were performed using funding from the Concrete Masonry Chekhov program through the Department of Commerce. So with that, I want to conclude my talk and see if there are any questions.